linguistic theory behind Blockly languages. So, Robin, please.
So, hello. In this talk, we first show you what Blockly languages are and what Blockly is. Then we look at some linguistic foundations, especially at some grammar formalisms for the definition of such block languages, and show how the mapping between the grammars and the block languages work. And at the end, we introduce some syntactic sugar and enhancements to some of these grammar formalisms to simplify the notation and also generate more complex blocks. So first of all, what is Blockly? Blockly is a library from Google to create such block editors like the one on the right-hand side here. And in a block editor, you don't edit the text in a free form like in a text editor, but instead you have each syntax element available as such a block here. And then you program by connecting these blocks together just like in a jigsaw puzzle. And by this, you are actually directly editing the abstract syntax tree of your program. And block editors like this are mostly used in learning platforms like Scratch or code.org. And one reason for this is that you can't make these classic syntax errors, like, for example, to forget the semicolon at the end of the line, or by completely forgetting this B letter here. Because if we would do this, then the user would directly see that there is a big hole in the program and sees that he has forgotten something. And if we compare this to a text editor, then you really would have to read the whole text to see where something is missing. And then you don't even know if the user tried to increment A or if the B letter is missing here. And if the user then now wants to fill this block input, he can refer to the toolbox where each syntax element is available as such a block, and he can then drag some of these blocks and try to connect them. And what's really nice now is that only these blocks will fit into the input that are allowed by the language. So for example, this return block or this comma separator won't fit into our block input, but this identifier block here will. And Blockly now really abstracts over this concept and allows us the creation of such toolboxes for arbitrary languages. For example, for general purpose programming languages like JavaScript, where we have function blocks or return block, and also for minimal languages like an expression language where we just have addition or multiplication blocks, or also some domain-specific languages like state machines where we could model our transitions on the start and the end state. So the question now is, if I have a custom domain-specific language, how can I tell Blockly which kind of blocks I want to have? Let's assume, for example, such an assignment block here and an identifier block. And for this, we have two options. We can directly define these blocks in JavaScript code or define them in a JSON object. And if we look at the JSON definition of this assignment block here, we see we first give this block a name, and then we define the message of the block, which is its visible part, which mainly consists of the equal sign here at the end, but also has placeholders for our two block inputs. And these placeholders are then defined in this arguments array, where we first specify which kind of placeholder this is. So input value stands here for block input, but we also have, for example, placeholders that could stand for this text input field here on this identifier block, or some drop-down fields and so on. Then we give our input a name. And the most important part here now is this check array, which is an array of no types that are allowed by this block input. And what Blockly then does is to compare this array with the output array of another block and check if they intersect or not. And if they intersect, so if they have a common no type, then they may be connected and otherwise not. But what you see here in general is that you really have to write a lot to define this simple assignment block with only an equal sign on it and two block inputs. So you can imagine if we have a whole language, then you probably have multiple hundred lines of code, and you can't just look at your definition and see at a glance what your language does. So what we want to do instead is to use the natural representation of the language, which is its grammar. And this has been done before for context-free phrase structure grammars. And if you now ask what are context-free phrase structure grammars, they are actually just the context-free grammars that you all know by Chomsky. But context-free grammar actually just says that this is a grammar that could create a context-free language. And of course, there are other grammar formalisms that could also generate context-free languages. For example, dependency grammars that we will see later in this talk. So we really have to call this grammar here by its full name, context-free phrase structure grammar, where phrase structure grammar is the term coined by Chomsky for his kind of definition with non-terminals and production rules of the regular context-free and context-sensitive grammars. So if we now look at the production rule here that could correspond to our assignment block, we see that this is much more compact. We have here the non-terminal on the left-hand side that corresponds to our block output, and the other two non-terminals correspond to our block inputs, and then the terminal corresponds to the text on our block. So we see this is much simpler, and this mapping has been shown before by Verano Merino and von der Storm. But what they also have shown in their mapping is that there are some inconveniences. And the main problem is that a production rule is not required to have terminals in them. So we also may have production rules without any terminals at all, and these then don't correspond to useful blocks. So this is really apparent if we look at the linguistic foundation where phrase structure grammars come from. So if we look at the sentence, this is a phrase structure tree in a context-free phrase structure grammar, and the analysis here, we really see where this name phrase structure grammar comes from. Because the sentence here mainly consists of two phrases, the verb phrase and the noun phrase. And then the verb phrase again consists of a determiner and a verb. So we see we have in the upper part all these non-terminals that are connected to each other, and then only at the bottom we have the real words of our language. And if we now take this structure here and directly map this to a block editor, we see since all these non-terminals here are non-terminals, they don't correspond to a word of our language. So we have now all these empty blocks that look exactly the same, or at least quite similar. So if you now try to build this program and construct this, you have to connect all these empty blocks, and you have to choose the right one, because otherwise they won't fit. So you probably agree that this is not that practical of a block editor, not really useful. And the reason for this is that what we see here is not a representation of our language as a block language, but instead we model here the meta language of our sentence. So what we really want to do is to, and have to do in the mapping, is to delete all these terminal-free rules from our grammar, which then means that our structures don't correspond anymore, which we will see later. So we really want to just delete all this, and it does not really help if we would add the names of the non-terminals here to the blocks, because now at least we could differentiate between them. But now you can't even see which sentence you try to model here, because you really have to know, you have only to read the words at the end on the right-hand side and ignore all this clutter in front. So we really just want to remove this, but if we would do this, then the blocks of our language would not be connected anymore, because at the moment they are just connected by the non-terminals. So what you have to do now is to decide for each phrase which word of the phrase is actually the head. So for example, the head of the sentence is the verb phrase, and the head of the verb phrase is the verb. So maybe you know head-driven phrase structure grammar, where you also have the concept that each phrase has a head. So this means now that this verb is should actually be the root node of our block editor. So if we now model this, we see again, if we read from top to down and from left to right, the sentence, this is a dependency tree. But now we don't have a phrase structure anymore, because what we do instead is to directly now model the dependencies between these words. And if you now compare these structures, you see they don't look any more similar. So phrase structure grammar is actually not that good of a formalism for the definition of block languages, because what you're trying to do in a phrase structure grammar is completely something different. You don't want to model phrases in your block language, but you want to model the dependencies between the words of your language. And that's actually exactly what a dependency grammar does. So if we now look at this syntax tree of a dependency grammar of the sentence, we see we don't have any non-terminals here, because what we do instead in a dependency grammar is to just model the dependencies between our words. And if we now compare these structures, we see they look exactly the same because they try to model exactly the same. So the question is now, why should we use phrase structure grammars for the definition of block languages if they model something completely different, while instead dependency grammars model exactly what we want to do? And if we now look a bit at the history, we see that dependency grammars are even a bit older than Chomsky's phrase structure grammars. The father of modern linguistic dependency grammar is Lucien Tenière, and especially his work Éléments de syntaxe structurale, which is a book about syntax that is completely based on this dependency grammar. And if we look at the publication years, it does not seem that Chomsky's work should be the younger one here. But the reason is for this is that Tenière's work was only published 5 years after his death, and he started his work more like in the 1930s, when Chomsky was still a child. And the concept of dependencies between words is even older. It was already present in the earliest known and preserved grammar by Panini in the 4th or 5th century before Christ. And the term dependency was first used in the 12th century AD. So what we're trying to do here is not to introduce something new, but we just notice that the structure in block editors actually correspond to this age-old formalism of dependency grammar of linguistic. And if we look at linguistic, we see that dependency grammar is a big alternative to phrase structure grammars by Chomsky, while in computer science, they are not really that well known and only used in natural language processing or computer translation. And some aspects of dependencies between words are nowadays visible in large language models, but in general, in computer science, dependency grammars are not used at all, which really is a pity because there's much theory behind them in linguistic. And the first who really gave a mathematically precise definition of these dependency grammar were a few years later Hayes, Gaveman, and Robinson. And what's nice is that they were not only the first to formalize dependency grammar, but to also show that their formalism is actually weakly equivalent to phrase structure, context-free phrase structure grammar by Chomsky. And what weakly here means is that if you have a dependency grammar, you always have a natural corresponding context-free phrase structure grammar where your syntax trees also look the same. But if you go the other way around, you don't have this natural correspondence because you have to make some adjustments and your syntax trees then don't correspond anymore. But still you could create the same set of languages, the context-free languages. But you see a similarity here in the mapping that you have to make these adjustments if you start with a context-free phrase structure grammar and go to a dependency grammar or to a useful block editor. So if we now look at this formalism by Hayes and Gaveman, we see this mainly consists of two concepts. The first concept is that we group words that behave syntactically exactly the same into some categories. So what this means is that all these words here could occur at the same positions in a syntax tree and also have the same kind of dependence. So in a syntactic way, they behave exactly the same and we could then group them. And then we have multiple such categories, for example, an assignment category with an equal sign, or a name category that accepts an arbitrary identifier as a word. And the other concept of dependency grammars are dependency rules, which look quite unfamiliar at first, but which mainly could read like a term definition or a regular production rule. So that we have on the left-hand side here a head category, and in the body here we have some our dependent categories. So this assignment here has two dependents, a name and an expression, and each dependency rule has such a triangle. And this triangle marks the position of the word of the category, so in this case the equal sign, between its dependents. So the equal sign stands between the name and the expression. And in general, the format is that we have a head category on the left-hand side here, and then in the body we have first some arbitrary amount of left dependents, followed by the word of the head category, and then some right dependents. So for example, the declaration category has no left dependence, but is directly followed by a word of the assignment category with all its dependents, and then at the end we have a semicolon. And if we now take such a dependency grammar and map this to a block editor, we make this just by taking each dependency rule and mapping this to a corresponding block. So for example, this assignment rule here corresponds to a block where we have a block input for a name. Then we have another block input for the expression, and in between we have the word of the category, which is the equal sign. And the same is true for the other rule. So we have a block input for an assignment block here, which means that this assignment block here will fit into the input. At the end we have a block input for a semicolon. But the difference now is that this category has multiple words, so we don't map this to a static string like with this equal sign, but instead we give the user a choice which one of these words you want to use and map this to a drop-down field. So if we compare this now to the JSON definition of the blocks, we see that each dependency rule firstly corresponds to such a definition, and the body of the rule corresponds to the message string of this block, and the word of the category corresponds to the text on this block. And we use the head category as the name of the node type of the output array, and the other category names, the names of the dependents, we use for the node types in the arrays of the connection checking of this block input. So what we see is that dependency grammars really directly model what we want to do in a block editor, and that also this mapping is extremely direct. But what's really nice is that we could make this even better if we introduce some syntactic sugar to dependency grammars that is also present in, for example, in phrase structure grammars by Chomsky that we introduced there. And by this we could then generate more complex blocks, like for example blocks with multiple texts on them, or blocks with multiple items in these connection arrays, because at the moment each array only has one single item in them. So the first thing that you notice is that most of the time, if you define a programming language here, then there is that all your categories only have a single word in them. So it does not really make sense to split this declaration here, and we allow to just inline the word directly into the rule, which then also look a bit more similar to a term definition or a production rule. And the next thing that you notice is that you sometimes have constructs like do, while, or ternary operator, or left and a right brace or bracket, so multiple words that actually are part of the same concept, which is visible that this right bracket here occurs only at one position as a dependent, which is here in the left bracket. So what we allow then is to just inline this rule directly into the parent, which again simplifies the notation of our dependency grammar. but now also gives us the option to generate blocks with multiple words on them, because we now have multiple strings here. And the last thing that we want to show is that you sometimes have constructs like you could print an addition, you can print an identifier, you can print and so on. So you really have the same rule multiple times, which is really tedious to write if you have that a lot. And the same problem we also have in production rules in context-free grammars. And what we there have done is to introduce this EBNF notation that you could print an addition or an identifier. And the same we could introduce now for dependency grammars. And what's nice about the syntax is that we now could take these multiple items here and map them to multiple items in the connection array of Blockly. So we see in Blockly, we actually have the same syntactic sugar. We could define multiple blocks with a single item in them, or combine these blocks to one block with multiple items. Yeah, and then there's more in the paper, which we won't show here. But what we have seen is that dependency grammars are describing exactly what we want to do in a block language, and that they are a strong contender for a meta theory of block languages, and probably also in other applications in computer science, especially in the field of software language engineering. Thank you.
Thank you. It was very, very excellent. So questions from the audience? Thomas.
Thank you very much for this interesting talk. I wonder to which extent you implemented this and perhaps automated also conversion from well, one type of grammar into the other and the other way around?
We have not implemented a mapping from context-free grammars to dependency grammars, but from dependency grammars to these block languages. So all these blocks that we see here are generated from dependency grammars. And I don't know, I think that there are not any automatic tools to map context-free phrase structure grammars to dependency grammars, but there are some mechanisms how to do this in the proofs, how, of Hayes and Gaveman, where they showed that the languages are equivalent.
Yes, exactly. And given that, of course, a lot of DSLs are defined, or languages are defined using grammars, I was thinking that this could be an interesting strategy to pursue. Did you consider this option?
I'm considering this because I'm considering if it's worth to formalize this proof, and by doing this then also to automating this. But what we are now actually at the moment are trying to do is, what we have done here is to just look at the syntax, and we are considering to implementing some semantic aspects. But you're right, since all grammars are actually defined in context-free phrase structure grammars, this would be good, but what we're suggesting here is more like for if you want to define a new language, that you then probably not should not start with a phrase structure grammar, but perhaps with a dependency grammar directly, because then you also could directly model how you want these dependencies to look like. Because if you start with a dependency grammar, then you have to decide which dependent is the head. So this is arbitrary, and you have multiple possible mappings then.
So is your advice then that language workbenches should implement?
Probably too, yeah.
Okay, thank you very much.
Maybe to follow up on that, it sounds like maybe you would be proposing dependency grammars as a sort of an abstract syntax representation. Is that a fair thing to say?
Because you're by this directly have the abstract syntax and don't have to make this mapping then afterwards.
Yeah, okay. Because I guess when you started, you see the blocks in some of it. I initially see abstract syntax there.
Yeah.
And think, oh, it's abstract syntax with a few terminal symbols to give the nice name. But that's not it at all.
So yeah, this was the point that in Blockly you are actually directly editing the abstract syntax, and so dependency grammars describe this.
Yeah, exactly. Yeah. Very interesting. So, all right.
This is very nice, and I've never actually heard of dependency grammars before. So a big problem with the idea of structure editing in normal textual editors is just the fact that it amounts to a lot of tree manipulation of the AST. It seems to me that maybe a dependency grammar is a flatter tree and therefore is more easily manipulated structurally. Has anybody tried that?
I'm not aware of this, but I think so too.
Okay, thank you.
Any more questions?
All right. If not, we'll thank the speaker. Then I have one thing to say after we thank our speakers. All right. Thanks again, Robin. As Ralph mentioned before, there is a plan for dinner tomorrow night, so we'll be leaving from 6 o'clock in the lobby of the hotel. If you've not yet signed up, you have just officially missed the deadline, but of course this is an artificial deadline. If you want to go, talk to me or sign up. Try and do that soon. If you had issues with the website or something, just come talk to me now and we'll make sure you get you on the list and we'll be ready to go. So, all right, thanks again, everyone.